Now this board, the next 4 sessions, 8 squares, two squares per session, 2 main themes. We're doing mathematical tools for the course, setting ourselves up with the math tools that we'll need and use for the rest of the course, the remaining 400 pages. And this board, these 4 sessions, the theme, the 2 main ideas. Not difficult. I think you'll breeze through these few sessions without any real trouble, unless it's completely new to you, in which case there's a lot of definitions that you'll have to memorize, and that's unavoidable, I'm afraid, if you want to understand the terminology in the remaining course. So 2 main ideas, two mathematical objects, if you like, we'll talk about. The first one is graphs. What is a graph? Now, it has a technical meaning. It's not the usual graph that you draw on a blackboard, curved lines and stuff. It's not that kind of graph. It has a technical meaning. We'll explain it in the next few sessions. And the second one is strings. Strings of characters, like a binary string, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 0. It's an example of a string of characters, in this case binary characters. So graphs and strings. But before I start on graphs, first one, I need to finish off a little bit of work from the previous session, which was on equivalence relations, and actually give you an example. Can you remember what an equivalence relation is? Well, firstly, what is a relation? Well, a relation is a predicate of a particular kind. What's a predicate? No, I'll assume you know all that stuff, right? Okay, so here's an example of an equivalence relation. Alright? And this relation operates on a particular set, and in this case the set is big N. In other words, the natural numbers, the positive integers, the counting numbers. There's lots of ways of labeling big N. Okay? So we're going to apply this equivalence relation to the members of big N, and we write this equivalence relation this way. It's just an example. So example 0.11, and here's the symbol for the equivalence relation. Usually generalized, the equivalence relation generalizes capital R, big R, but in this case it's sort of a three bars and a suffix 7. And what does that mean? Well, two natural numbers, I and j belong to n, obey this equivalence relation, this relation, if the difference between them, when you subtract one from the other, that difference is a multiple of 7. Saying that another way, you can divide, without remainder, you can divide the difference between them by 7. Okay? Now, why is this relation here? Why is it an equivalence relation? Now, remember from the previous session, an equivalence relation is a special kind of relation that obeys 3 properties. It's a rather restrictive kind of relation, and those 3 properties, if you remember from the previous session, were the relation has to be reflexive, symmetric, and third one, transitive. And reflexive means that x, whatever whatever it is that you're talking about. Well, in this case, in the context of big N, so the x would be a natural number. So is x r x? In other words, is there a reflexive relation between x, like is x r x? Does that hold for itself? So in other words, if I put I here, I both sides, is that true? So in other words, then you'd get I minus I. Is that a multiple of 7? Well, I minus I is just 0. That 0 is a multiple of 7, right? You can divide, if you divide that difference, 0, by 7, you get 0 remainder. There'll be no remainder, so you can so it is 0 is divisible by 7. Okay. So in other words, when you have IR here, that works. So this symbol here, this relation is a reflexive relation. Okay. So it is reflexive. So we proved the first of those 3 criteria that we have to show are valid in order to show that that this relation, we don't know it's equivalent yet, that this relation is equivalent. We have to test it in 3 ways. Okay, so we've done it for reflexive. How about symmetric? Now, remember symmetric? So we've I'm just going to do a bit of revision. Symmetric. If this thing j and if this with j, in other words, there is this relation, this relation with j, then is it true that then j this relation with I, so you sort of reverse them, sort of symmetry, is that true? So if I r, well, r is this, so if I r j, does that imply j r I? That's what's meant by symmetric. Well, let's test it. Okay, so if I r j, you're told that's true, then the difference between them is divisible by 7. Okay, so that means this difference is 7 times some integer. Okay, because you can divide this by 7. So 7 will be a factor of this difference. So you can write I minus j as 7 times some integer. Right? Okay. Now how about j minus I? Well, if I minus j is sorry, should have been up here. So if I minus j is divisible by 7, it'll be 7 times p. So p is an integer. Let's just change one letter. Okay. So that implies that if you reverse this, if you multiply this by minus I, so you get j minus I equals minus p7. Right? You just multiply both sides by minus 1. So you'll get minus p7. Well, minus p, if p's an integer, minus p is still also an integer. Right? So that means that j minus I is also divisible by 7. Okay? You can divide 7 into this with 0 remainder. Well, so that means that j r I. So if I r j, then j r I. Okay, so it's symmetric. Okay, now how about transitive? What can you remember what transitive was? So if the transitive property is if I r j and j r k, then if it's transitive, then I r k. Okay, Let's say it again. If I are j and if j are k, then that r is transitive if I are k. Right? So we have to show that this is transitive now. All right. Let's see. So you're told I are j, so that means that the difference is divisible by 7. So I minus j is 7p, p some integer, and you're told that j r k, yeah, that's true. So that means the difference of these two can be divided by 7. So that means j minus k equals 7q. Q is just some integer. There's like the p here, right? Now here's the trick. We're trying to show that I